Hi, this is Ken Johnson for another episode of SecCast. This tutorial is part 2 of a two-part tutorial on broken authentication and session management, or OWASP's Top 10 2013 A2 category. While part 1 of this tutorial covered session management issues, part 2 will instead cover broken authentication weaknesses. We'll discuss weak password complexity, username enumeration, brute force credential attack prevention, and insecure forgot password functions. Let's get started. Password complexity relates to the requirements placed on users' passwords in order to enforce a certain level of strength against password guessing attacks. This is why sites require at least 6 characters, possibly upper and lowercase characters, etc. Password requirements should not be restricted to just digits, special characters, and length, but also that certain keywords are disallowed as well. For example, we are attempting to sign up as user test1@test.com. We'll enter a password of password and repeat this in the password confirmation field. Because this shows a successful sign-up, we know that the password requirements are not strong enough. You should never allow the word password in any form, meaning prefixed or appended with other values such as letters or numbers. If you've built custom authentication, that is to say not using an authentication library such as Devise, you can validate user complexity using the format method in your user model. We'll use the validates method on the password attribute, specify format with, and pass in a regular expression that our password must match. I should warn the regular expression we show may be too strict for use in some sites, so I recommend creating your own regular expression. If you leverage Devise to handle authentication, you can start improving complexity in the Devise configuration file by leveraging the password length method and supplying a minimum and maximum digit count. Here we show a configuration that has a minimum requirement of 8 characters and a maximum of 128. Next, we'll use the validate method if the user is setting the password. The secure password method is called if this is the case. We create a definition for the method secure password, call the password complexity method, and assign a receiver of PC. If PC is false, we trigger a Devise error. The password complexity method has a set of regular expression checks. If any one of them fails, the validation fails and adds a Devise error. The first check looks for a lowercase alphabet character. The second check is for the presence of uppercase characters. The third check is for the presence of a digit. The final check is to ensure that the word password is not present in the password object. Now, every time a user goes to set their password, this validation will be run against that password in order to enforce password complexity requirements. Username enumeration occurs when error messages, deviation in application behavior, or variances in timing indicate whether or not a username or email address exists on a system. For instance, we will attempt to authenticate with an email address that does exist on this system. However, we will provide an incorrect password. And as you can see, we provide an invalid password, submit these credentials, and review the response. In the response, you can see an error that indicates our password is incorrect. This may indicate that a user exists on the system. Let's enter an invalid email address and compare the responses. As you can see, after entering an email address that does not exist on the system, the response indicates that the email address does not exist. This is a very simple and obvious case of username or email enumeration. Another common place to see this vulnerability arise is in sign-up pages, forgot password functions, and account update pages. As you can see here at the sign-up page, it is usually an error that indicates a user with that username or email address already exists. Instead, an email could be sent to the legitimate account holder notifying them that they have already signed up for an account, and if they were not the individual responsible for triggering this message, they should contact the application owner. Again, a similar problem and solution here at the Forgot Password page. To reiterate, the application is vulnerable if variations exist in the way the application responds when a username or email address exists and when they do not. The risk is that an attacker will leverage this weakness to collect email addresses, which can be used for guessing login credentials to the site or phish the application's users in a targeted way. Prevention can be fairly straightforward. Firstly, provide the user with generic error messages that do not explain whether or not the email address or username entered is correct. Secondly, if, for instance, a sign-up page redirects to another page after successful submission and shows a message such as a confirmation link has been sent to the following email, continue this behavior even when an email address already exists on the system. This prevents deviation in behavior and does not alert an attacker to the presence of a valid email address or username. Lastly, using constant time comparison functions such as secure compare to prevent timing attacks. Let's demonstrate. One thing I'd like to mention, please ignore the use of MD5 hashing in this code example. It has no bearing on this tutorial, and just as a reminder, this is a purposefully vulnerable application, and so it intentionally uses a poor hashing algorithm to store passwords. All that aside, there are two separate items here I would like to point out. Firstly, notice we perform a password comparison only if a user has been found by the email address they've provided, meaning no additional computation is required, or in other words, there is no further code execution if the user cannot be found in the database. This is our first weakness. The second weakness is that we leverage the double equal operator to perform a comparison between the password hash stored in the database against the password supplied by a user. In order to prevent a timing attack both against username enumeration and password cracking, we should do the following. 1. If a user cannot be found in the database, make a temporary user object. This allows your application to continue executing the same code as it would if the user existed in its database. There would be no difference in the time it took for the application to respond in this instance. Secondly, leverage the rackutil's secure compare method in order to prevent against timing attacks. Timing attacks might allow an attacker to guess each individual character of the password hash based on differences in the time it takes to perform the comparison between a user-supplied password and the password hash. To recap, you can prevent username enumeration by providing generic error messages, non-deviation in application behavior, and the use of constant time comparison functions. Brute force credential attacks are basically a fancy way of saying someone is automating the task of guessing username and password combinations. If the site does not take precautions to protect itself, at the very least user accounts could be broken into. The extent of the damage, the risk associated with certain levels of privilege between certain accounts, those are other factors that help determine the overall risk. Again, at the very least, it's probably a bad thing to allow your site to have this vulnerability, so let's briefly cover what the attack looks like and then delve into prevention. First, we'll make a request with a known bad password but correct email address. Next, we'll catch that request in our intercepting proxy, right-click on the request, and forward to our intruder tool. For those who haven't watched our other videos, Intruder automates sending requests in addition to some other features such as substituting values with other values, which is why you see us put an insertion point around the password here. We are going to send this same request over and over again, trying a different password each time. So we'll choose a password list and add the correct password so that it is the very last password to be submitted. Finally, we'll bump up the amount of threads or simultaneous requests we'll make and start the attack. Now that the attack is run, it's time to review the results. We have two columns that are of particular interest in this exercise: response code and byte length. We'll reverse the sort order so that we can see the last request first. Note that while all the other requests seem to have a 200 response code, the last request has a 302 response code and a variation in the byte length of the response. Upon a review of the response, you can see that we are redirected to the user's dashboard, indicating this login request was successful. One thing to note, since we are using an automated tool for this attack and not a browser, it is possible for us to strip the session cookie from the request. Basically, it is not a good idea to base lockout decisions on the session provided by the user, since it can be removed from the request. There are three primary ways that developers prevent automated attempts. All of them add value. Which one you choose is up to you. We'll explain each. Firstly, throttling attacks for the login endpoint is always an option. Libraries such as RackAttack assist in this effort. Remember that if the source IP is the only factor used when determining who to throttle, attackers can hop from one IP to the next, so you should leverage other factors as well, such as request headers, email or usernames submitted, etc. Secondly, CAPTCHAs are an easy solution so long as you use a standard CAPTCHA solution and do not attempt to develop one yourself. I highly recommend reCAPTCHA. Thirdly, if you are using Devise, we'll demonstrate how to configure Devise to prevent account lockout. If you're going to create your own account lockout implementation, I highly recommend reviewing how the authors of Devise go about solving this problem and replicate the solution. We are reviewing the Devise configuration file typically located under config/initializers devise.rb. The first thing you may notice is that we choose the strategy of failed attempts for our lockout strategy. Secondly, we'll use the email attribute to make that determination, but if you're using another attribute such as username, you would want to change this value. Thirdly, we use both a time-based as well as manual unlock strategy indicated by the both attribute. Time-based means that following the last failed login attempt, and after a certain period of time defined below on line 182, the user's account will automatically be unlocked. Manual unlocked means we go in and handle that ourselves. Finally, maximum attempts relate to how many failed attempts are permitted before the application locks the user's account and they are unable to authenticate. One last piece is paranoid mode. This will help prevent username enumeration by protecting the unlock and password reset functions, but will not assist with the registration function baked in by Devise. Our final topic is insecure forgot passwords. The following are a few basic rules to follow. Besides username or email address enumeration, you should also avoid emailing a plain text password to a user, as their email could be compromised, especially if they are on a mobile device, for instance. Access to email and authentication into an application are too closely tied together. Additionally, do not allow guessing of security challenge answers, much in the same way we want to prevent credential guessing. To give a visual demonstration, you can see our fake mail service, mail catcher. Our inbox is empty. Now let's navigate over to the application. We'll type in a valid email address at the forgot password function, and here you can see that the password is presented in plain text. Avoid doing this for the reasons mentioned previously. Next up, we navigate once again to the forgot password function, but instead we are asked for our email address and security question. This too can be automated in terms of guessing the correct answer, so consider using some of the same prevention techniques we discussed in the brute force credential attack section of this tutorial. Email or SMS are channels that are considered out of band because you must access another service outside of the application in order to perform some action, or in this case, reset your password. Inline means you are performing the reset without leaving the application. When using the inline medium, again, implement the same protections we mentioned for authentication. When using an out-of-band medium, send a link to reset the user's passwords that can only be used once. The link should not be usable after a certain period of time. Leverage a strong library such as Secure Random to generate reset tokens, and require a security question challenge in addition to all of the other steps previously mentioned. To recap, we've discussed and demonstrated weak password complexity, brute force prevention, username or email enumeration, and hardening of password reset functions. I'm Ken Johnson. This has been another episode of SecCast. Thanks for watching.